Bismillahirrahmanirrahim is a continuance of our calculations involved in preparing isotonic solution. Today we will discuss another method of isotonic solution preparation. How we can calculate the quantity or weight of electrolyte and non-electrolyte and electrolyte needed to prepare isotonic solution. So previously we have discussed a very simple method for of that freezing point depression method. In which method 1, which there was a simple formula for a percentage weight in volume of substance needed to prepare isotonic solution. It was equal to 0.52 minus A divided by B. This was the freezing point of lacrimal secretion, and this A was the freezing point of unadjusted solution, and this B was the freezing point of adjusting solution. Now we will today we will discuss also another way of freezing point comparison method, freezing point depression comparison method to prepare isotonic solution. Before discussing this method, we should know that in this freezing point depression methods are these cryoscopic methods. We find the freezing point of isotonic solution and compare it with the freezing point of our another solution, and when the freezing point of both isotonic solution are our blood and lacrimal secretion, it become equal to the freezing point of our injectable or I solution. We say that our injectable or I solution preparation is also isotonic. Here we will discuss it. Generally it is accepted that what is accepted? Generally it is accepted that freezing point depression of blood and lacrimal secretion, that is isotonic solution, is equal to 0.52 degree centigrade or minus 0.52 degree centigrade. That is, if suppose it is the scale of our thermometer, it is 0 degree centigrade, pure water will freeze at this 0 degree centigrade, but our blood or our lacrimal secretion, they will, it is minus 0.1, they will freeze at a bit lesser temperature than this of pure water, that is 0.52 degree centigrade. They will freeze somewhere there at 0.52 degree centigrade. So another solution, if we prepare, we add for example, this is pure water. When we will add pure water, it will obviously freeze under normal condition at 0 degree centigrade. If this is our blood, this will also this will freeze at a 0.52 degree centigrade, minus 0.52 degree centigrade. But if we take this is another example of for example, we prepare a solution like this, which will also be isotonic. So this is for example pure water. By adding some solute to this pure water, which may be electrolyte or non-electrolyte, electrolyte, as we know that it passes current and it dissociates into positive and negative ion. Non-electrolyte, it doesn't passes current and it doesn't dissociate, or it has negligible dissociation properties. Electrolyte are for example sodium chloride, and non-electrolyte are for example boric acid, urea, etc., potassium chloride. So if we add these substances to this pure water, its freezing point will also be decreased or depressed from 0 to up to some minus 1, minus 1.86, minus 2, or minus 0.52 degree centigrade. But we will add this non-electrolyte or electrolyte to this pure water till its freezing point is decreased to minus 0.52 degree centigrade. Then we will see that both this blood and this solution have equal freezing point depression, or they freezes at equal temperature, that is 0.52 degree centigrade. So if this is isotonic, then our solution will also be isotonic. For this we need some hypothesis. There is a hypothesis which says that when one gram molecular weight, 1 gram molecular weight mean 1 mole of non-electrolyte what is meant by non-electrolyte, as I have discussed and clearly here, that a substance which gives negligible dissociation. Negligible dissociation mean which negligibly dissociate or breaks into positive and negative ions. For example, boric acid, when it is when 1 gram molecular weight is dissolved in 1000 gram of pure water, then it will decrease or depress or lower the freezing point of a solution, and it will have a freezing point depression of 1.86 degree centigrade as compared to that of pure water. It is 0 degree centigrade. So by very simple proportion we can find the exact quantity that is required to produce this 0.52 degree centigrade freezing point depression. We know that what is the molecular weight of boric acid. Here we discuss it again and again that it is non-electrolyte. It has negligible dissociation. It doesn't dissociate into positive and negative ion because osmotic pressure or tonicity is mainly dependent upon, not only dependent upon the quantity but also on the particle, because it is a colligative property. It depends upon the particles which are present in this solution. So if there will be non-electrolyte, it will not dissociate into particle. If we for example add 100 molecule there in this solution, there will be 100 particle in this solution of non-electrolyte, and there will be a freezing point depression, let's suppose of 1 degree centigrade. But if we will add 100 molecule of electrolyte, a bimolecular biatomic or binary ion are producing 2 ion electrolyte, that is one molecule produces 2 ion, then these 100 particle, when they will be dissolved in this solution, they will produce 200. When these 100 molecule are dissolved in this solution, they will produce 200 particle. So obviously the osmotic pressure or tonicity produced by these 200 particle will be more as compared to that which was produced by the 100 particle, 100 molecule of non-electrolyte. That is, it will produce for example a 2 degree centigrade decrease as compared to 1 degree centigrade decrease or depression which was produced by the non-electrolyte. So we discuss again and again that now we are going to discuss the non-electrolyte quantity which is required to produce isotonic solution. Molecular weight of boric acid is 61.8 gram. That means that 1 gram molecule or 1 mole. The weight of 1 mole of boric acid or 1 gram molecule, 1 gram molecule of boric acid, 1 gram molecule of boric acid has a weight of 61.8 degree centigrade. Here we discuss that 1 gram molecular weight or 1 gram molecules or 1 mole of anything is added to 1000 gram of water. It will produce a freezing point depression of 1.86 degree centigrade. So we say that 1 gram molecule molecules are 1 gram molecular weight, that is 61.8 gram 61.8 grams, sorry, when it is added to 1000 gram of water, it will produce a freezing point depression of 1.86 degrees centigrade. But we are concerned with a freezing point depression of 0.52 degrees centigrade. What will be the quantity of this boric acid required to produce this much freezing point depression? Because we are concerned with this, because 0.52 degree centigrade freezing point depression is the freezing point depression of a blood or isotonic solution. For proportion, you can also see my lecture on proportion. Here I will discuss it in a short way, that is the freezing point depression of 1.86 degrees centigrade is more than the freezing point depression of 0.52 degrees centigrade. So freezing point depression is decreasing, and if 61.8 gram of boric acid is needed to produce 1.86 degrees centigrade freezing point depression, then obviously for 0.52 degrees centigrade a lesser quantity of boric acid will be needed to produce 0.52 degrees centigrade freezing point depression. So we will write it in this way according to the rules. This arrow side will be written in the at the top. X divided by 61.8 is equal to 0.52 divided by 1.86. By cross multiplication, we can find 1.86x is equal to 61.8 multiplied by 0.52. Dividing both sides by 1.86, we find that x will be equal to 17.3 grams of boric acid. So it means that 17.3 gram of boric acid, if they are added to 1000 gram of pure water, they will produce isotonic solution. Why? Because they will produce a freezing point depression of 0.52 degrees centigrade, which is the freezing point depression of blood or lacrimal secretion, which are considered isotonic, or which are actually isotonic solutions. From this we can find a common or general equation that if x is the x is the weight of a non-electrolyte needed or to be added to 1000 gram of water to produce isotonic solution, and 61.8 degrees 61.8 is what? It is the molecular weight of a non-electrolyte. Multiplied by 0.52, it is the freezing point of a blood or lacrimal secretion, which are actually the isotonic solution, and it will be divided by 1.86, which is the freezing point depression of a non-electrolyte. It was a simple method for determining the weight of non-electrolyte needed to produce 1000 gram of isotonic solution from pure water, that it can be generalized for any other substance of or any other non-electrolyte substance, rather I should say that molecular weight of non-electrolyte, whatever it's so, multiplied by 0.52 divided by freezing point depression of non-electrolyte, which is given, which is known. Freezing, what should be the freezing point of a non-electrolyte? This should be the freezing point of non-electrolyte having a weight of 1 mole, and it is usually given in the literature, so we can find the weight of non-electrolyte needed to produce isotonic solution. In short, we can say that 17.3 gram of boric acid and 1000 gram of water that is, it will be a weight and volume strength of 1.73%. It will produce isotonic solution, and this solution will be having a freezing point depression or decrease in freezing point of 0.52 degree centigrade. Now we are going to discuss the quantity or weight of electrolyte. Needed to prepare isotonic solution. How we will find this quantity of electrolyte needed to prepare isotonic solution? It is very simple, but there is simple point which we should understand. As I discussed earlier, that if this is pure water, it has a freezing point of 0 degree centigrade. Now if this is a pure water and we have added here for example 100 molecules of non-electrolyte, if let's suppose it has decreased the freezing point from 0 to 0.5 degree centigrade, we have added this non-electrolyte. For example, it was boric acid. It was boric acid. Now if this is another solution, same volume, and we have added here electrolyte, for example sodium, 100 molecules of sodium chloride, which is electrolyte. Same 100 molecule of boric acid were added. Now sodium chloride has is a weak electrolyte and it has 80% dissociation. What does this mean? This means that out of 100 these 80 molecule will divide into 2 and there will be 180 molecules. It is 80% dissociation. So instead of 100 molecule here, 100 particle, there were 100 molecule and 100 particle there. They were having isotonic or isotonicity of 0.050 degree centigrade. But now there are 100 molecule but 180 particle here. It means that the number of particles are increased here. As osmotic pressure is colligative property, it means that it depends upon the number of particles. So the number of particles, as we see that here, are increased. There were just 100 particle here, but here are 180 particles. So it will have more effect on the osmotic pressure, and osmotic pressure will be decreased less. It will be decreased up to, for example, up to minus 1 degree centigrade. So we can see that this dissociation factor I, which is equal to the total number of particles but produced by the actual number of molecule, it will be 1.8. This is the dissociation factor. This factor must be included because it affects our osmotic pressure or our freezing point depression. In this way, so it must be included in the calculations equation. So if we consider that 1 gram molecule that is 58.5 gram of sodium chloride, if they are added to 1000 gram of water, what will they do? They will cause 1.86 1.86 degree centigrade depression multiplied by the dissociation factor I. So what will be the freezing quantity of sodium chloride needed to produce this much 0.52 degree centigrade? From this we should know that as 100 molecule of boric acid produces this much osmotic pressure and this much freezing point depression, and the same 100 molecule of electrolyte like sodium chloride, which will divide into 180 particle, it produces this much of freezing point depression. So from here we know that to produce 0.52 degree centigrade of freezing point depression, so by simple proportion we can find this quantity. It will decrease because 0.52 degree centigrade is lesser than 1.86. Obviously the quantity of or weight of sodium chloride needed will also be decreased. So you will write it in such a way: x divided by 58.5 is equal to 0.52 divided by 1.86 by cross multiplying, multiplied by this dissociation factor I. So 1.86 multiplied by I multiplied by x, it will be equal to 0.52 multiplied by 58.5. X will be equal to 0.52 multiplied by 58.5 divided by 1.86 multiplied by dissociation factor I. So what will be the quantity of X? X will be equal to 9.09 gram. So we can see that in case of boric acid, this X was equal to how much? This X was equal to 17.3 gram, because boric acid is a non-electrolyte. While in case of electrolyte, sodium chloride, the quantity of sodium chloride needed to produce isotonic solution, which will be having a freezing point depression of 0.52 degree centigrade, is a 9.09 gram. It is less than 17.3 gram. Why? Because sodium chloride is 80% dissociable, that is 80% dissociate, and 100 molecule of sodium chloride will produce 180 particle in the solution, and they will produce a more tonicity and will give more tonicity as compared to the 100 particle of boric acid. So we can generalize this formula. It is the weight of electrolyte needed to produce isotonic solution is equal to molecular weight of electrolyte multiplied by the freezing point of blood or pure water or lacrimal secretion, which is 0.52 degree centigrade, divided by the freezing point of freezing point depression of 1 mole or 1 gram molecules of electrolyte. It is 1.86. Molecular weight is 58.5 multiplied by the dissociation factor I. This dissociation factor is different for different electrolytes. It can be found in such a way. For example, if sodium chloride is 80%, is having 80% dissociation, what will be the number of particles total? 80% mean that out of 100 molecule, 80 molecule will dissociate, and they will produce 80 sodium ion, 80 chloride ion, and there will be 20 undissociated ion. So total number of particle will be 180 particles. And what will be the I, dissociation factor? dissociation factor will be total number of particle divided by actual molecule. It is 1.8. The dissociation factor is different for different substances. For non-electrolyte and substances of slight dissociation, this is one. Substances that dissociate into two ions. Electrolytes having two ions. The dissociation factor for such electrolytes is 1.8, and electrolytes dissociate into three ions. Dissociation factor is 2.6. Electrolytes that dissociate into four ions. Dissociation factor for them is dissociation constant is 3.4, and substances that dissociate into 5 ions, their dissociation factor will be 4.2. Thanks for watching.